In this video, we're going to go over rules for how to write acid-base reactions. So for step one, we're going to list all of the species present. So all strong acids must be ionized into two ions. So one of them is going to be hydronium ion, so we need to correct this. This does need to be a superscript plus sign. So it's very important that you write hydronium and not H plus ion, okay, because we are going to be using the modified Arrhenius acid reaction, so just where you have your acid reacting with water in order to create these two ions. So you need to be writing your hydronium ion as one of your two ions, and then your remaining ion will be the cation or the negative ion. So for example, let's say we had something like perchloric acid, so that's HClO4. So how we would ionize that, right, is we would write out the compound. Acids are always aqueous, and then the two ions it would break apart into would be hydronium, and that's coming from reacting with water. So we would have hydronium as one of our ions, and how we get hydronium is if one of these hydrogens goes away from our acid towards water. So then you just look and say, okay, well, perchloric acid with one less hydrogen in it, well, that's just ClO4, and it'll have a -1 charge. Okay, so that's how you'd figure out what your two ions are. Just react your strong acid with water, and what your products are what you have to list. Now, all soluble ionic compounds must be dissociated into two ions. So how you can tell if an ionic compound is soluble is you can look at the solubility table on page 6 of your data booklet. So with this, what that solubility table looks like, so let's go to page 6. So this is the solubility table that I'm referring to. So let's say that we have an ionic compound such as sodium chloride. So how you're going to start out with finding this compound in your solubility table is you usually start with your anion. So in this case, chloride is the anion. So if I find chloride and trace my finger down, most things with chloride ions are soluble, but you do just need to check the last row just to make sure your cation isn't one of the exceptions. Since I don't see sodium in the last row, that means it does fit under most, so it is very soluble in water. If a substance is very soluble in water, then it's going to break apart into its ions. So sodium chloride aqueous breaks apart into sodium ions and chloride ions. So whenever you write dissociation equations, you're always going to get only two products, the cations and the anions. If you're breaking it up any further, you're not doing a dissociation reaction correctly. Okay, so weak acids and molecular compounds, they do not separate into ions. So those are going to stay together. So just as a reminder, ionic compounds are when you have a metal with a nonmetal. Molecular compounds are only made up of nonmetals. And weak acids, you can find those if you go to page 8 or 9 of your data booklet and you look in between the two gray lines. So where I've highlighted in green on both pages, that's where your weak acids are going to be found. All right, so that's step 1, list all of your species present. And then step 2, you're going to start at the top left-hand side of the table. So that's the table on page 8 and 9 of your data booklet. And then moving down, you're going to find the strongest acid, which is abbreviated to SA. So let's just write in here that we're talking about page 8 and 9 for steps 2 and 3. So basically, whichever acid you run into first, that's going to be your strongest acid. And then for step 3, you're going to start at the bottom right-hand side of the table, and then moving up, you're going to find the strongest base. So going from bottom to top, whichever base you run into first in the conjugate base column, that's going to be your strongest base. Then for step number 4, you're going to transfer a proton from the acid to the base to determine the product. So super key here that you're only transferring one proton. So remember, a proton is just an H+ ion. Step 5, you need to determine the appropriate arrows using using the acid-base table in the data booklet. So if you have your acid above the base, the products are going to be favored, or you're going to write the equilibrium arrows with saying that more than 50% of the reaction goes forward, okay, or more than 50% of the reactants react to produce products. Or if your acid is below the base, that means the reactants are favored. So you're going to write the equilibrium arrows and then say that less than 50% of the reactants react to produce the products. Now, if you're using a quantitative arrow, I typically just use the one reaction arrow going forward. So that means that most of your reactants react to produce your products. So typically, the situations in which that happens is you have a strong acid reacting with something weak, or if you're talking about bases, it would be a strong base reacting with something weak. But I just need to write this down here. So these first 2 points are talking about the relative positions of acids and bases on page 8 and 9. So with the quantitative arrow, what you're going to have in order to make you rate the quantitative arrow, or this arrow right here, is you're going to have hydronium reacting with hydroxide, or they just tell you in the question it's a quantitative reaction. Okay, so we're going to write the Brønsted-Lowry equations for the following reactions and determine if the products or reactants are favored. So we've got solutions of sodium hydrogen carbonate. So because sodium's a metal, and then I know hydrogen carbonate has nonmetals in it, we know that this is ionic. So we're going to have to dissociate it. Also, solutions, that word tells you that water is present. So first step, we need our species list. So we've got water. So I'll make that more obvious that it's subscript. And now we need to dissociate the sodium hydrogen carbonate here. One, because we're told we have a solution of it, and then two, so if I wrote this out, so we have sodium hydrogen carbonate. So if I found that in my solubility table, so we can't find hydrogen carbonate as our anion. So if that's the case, then you need to go to your cation. Now sodium, we find sodium right here. It's a group 1 ion. So that means when I look at my solubility table, sodium hydrogen carbonate fits under group 1 ions because sodium is a group 1 ion. Now if I trace my finger down, okay, most things with sodium are going to be soluble, but I need to double check if my compound is in one of the exceptions. So if I found my compound in this last row, it would be insoluble in water. However, since sodium hydrogen carbonate is not in the last row here, then it is very soluble. So that means that we need to dissociate it. So remember, we're only dissociating it into two things, the cation and the anion. Okay, if you want a list of polyatomic ions to help you with dissociating compounds, you can look at your periodic table right here. Where you would find hydrogen carbonate would be right here to help you with breaking up sodium hydrogen carbonate. Okay, the other solution we have is sulfurous acid. Okay, so sulfurous acid, we need to ask ourselves, is it weak or is it strong? Because that will determine if we need to list hydronium and the anion, so the negative ion, or if we keep it together. So is it weak? Is it strong? Right now we don't know. We need to find it on page 8 or 9 of our data booklet here. So what I'm going to do is I'm just going to turn this so it's a little bit easier to read. And then I'm also going to turn this one too. Okay. So sulfurous acid, I'm finding it right here. So because I've found it between the gray hydronium line and the gray water line, that means that it's going to be a weak acid, okay, because I find it in the acid column. So This tells us, yep, it's weak, so keep it together. So then I'm going to write it. That was H2SO3, and acids are always aqueous. Okay, so that is my list. So we've completed step number 1. Now we need to go to step number 2. So we're going to start at the top left-hand side of the table, and we need to find our strongest acids. So basically, we're checking to see which one of our species in our species list that we run into first in the acid column. So let's go back here, and keeping all of our species in mind, I'm putting my finger right here, tracing down, and it looks like the first thing that I run into is going to be that sulfurous acid. So I can label it as my strongest acid. So I'm going to label it as SA. Now, if you can't keep your entire species list just in your head, what I would recommend that you do is you could either circle the species right on your data booklet, or you could use little sticky notes to just mark them out once you have your species list completed. That may help you. Okay, so now we need to do step 3. So we need to start at the bottom right-hand side of the table, and moving up, we need to find our strongest base. So looking here, okay, I'm just looking to be like, okay, I need to keep my species list in mind as I'm going through the table here. So let's go to the bottom, okay, and then I'm placing my finger here, and I'm moving up the conjugate base column, and I'm going up until I run into my first base that's in my species list here. So HCO3, that was in my species list, and that was the first one that I ran into, so that is my strongest base. So now what I'm going to do is I'm going to take my strongest acid and strongest base, and I'm going to react them together. So here's my acid. Here's my base. So remember that acids donate their protons. So acids, A for away. So one hydrogen moves away from the acid towards the base. Okay, and for the reaction arrow, let's check out the table. So my base was there, so I've got it circled in blue. My acid was here, so my acid is above my base. So that means when acid is above the base, that means products are favored. So what I need to write, I'm going to write the reaction arrow as an equilibrium, and then I'm going to write the forward reaction here. So I'm trying to communicate that the forward reaction is favored here because I've got two weak substances, so a weak acid and a weak base. And since I need to communicate whether the forward or reverse reaction is favored here, that's why I need to look at if my acid is above or below my base here. So since it was above, forward reaction is favored. Okay, how you can help yourself remember that is if you draw a line in between your acid and your base. And if it looks like a ball could kind of spontaneously roll down it as they are, then you can assume the forward reaction is favored. Okay, so with the ball rolling down the hill, if you've already done the thermochem unit, that is an indicator that the forward reaction is a spontaneous reaction. So that would mean forward reaction is favored. Okay, so for predicting our products, so looking at sulfurous acid, 1 proton left. So I got to imagine it with 1 less hydrogen. So that would be HSO3, 1 minus. The 1 minus charge came from sulfurous acid initially had a neutral charge. It lost a 1 plus ion. So it lost an H plus ion. So 0 minus 1 is equal to -1. That's how I got the charge for this. All right, now for my other product here, we need to imagine this hydrogen carbonate ion with 1 more proton on it. So that would mean it would be H2CO3 aqueous, and it would be neutral because we start off with a -1 charge and we gained a 1 plus charge. So that's why it's neutral. Alrighty, and since I'm going to just label the conjugate acid and base here, so with our acid, remember acids are always paired with conjugate bases, and bases are always paired with conjugate acids. Okay, so that kind of goes above and beyond the question here, labeling the acid, the base, the conjugate acid, or the conjugate base. But I did just want to do that as a review with how to pick out conjugate acid-base pairs. Okay, let's do the next one. So it says determine the quantitative reaction. So that means we're going to be using the forward reaction arrow. That would occur when perchloric acid is added to, I think there's a typo here, added to a sodium carbonate solution. Okay, so quantitative, and we got perchloric acid. So let's start off with our species list. So we've got a solution, that means water is present. So I'm just going to get that out of the way because oftentimes water can be forgotten about. Okay, perchloric acid, that's one of our strong acids. So that's that HClO4. Now remember with strong acids, you need to ionize them. So funny enough, we already did perchloric acid. So I'm going to list hydronium ions and these chlorate ions in my species list. Okay, so perchloric acid is done. Now we got sodium carbonate. So sodium carbonate, that's ionic. And it does say it's a solution, so that's making me lean towards it is aqueous, so I do need to dissociate it. But let's just double check on here. So sodium carbonate, here's my carbonate ion. Okay, group 1 ions are soluble when they're paired with carbonate. And would you look at that? Sodium is in group 1. So sodium carbonate, we need to dissociate it. So it's going to break apart into its cation. So sodium and its anion, which is carbonate. And carbonate has a 2- charge on it. And how you can double check that is you can go to your list of polyatomic ions and you can find carbonate and it has a 2- charge on it. Okay, so that's our species list done. So with the tip that I mentioned above here, if you have trouble keeping all of your species just in your head, or if your species list is fairly long, what you can do is you can go to page 8 or 9 and either use sticky notes to kind of point out all of the species that you have, or you could just lightly circle it with your pencil, either or. Just want to clean this up a little bit first. Okay, so we've got hydronium. We also have water. I'm going to circle water down here as well. So what else do we got? We got hydronium and water, the chlorate ions. So let's circle those. So that's going to be right here. Sodium doesn't occur in this table, so we don't need to worry about it. And then the only other ion left was the carbonate ions, so let's find those. So here we go. Okay, so what I'm going to do is I'm going to take my finger and then scroll down. It looks like the first acid that I run into is the hydronium ions. So I'm going to label that as my strongest acid. Now for the base, I'm going to go back to my table and I'm going to put my finger in the bottom right-hand corner and then move it up. Looks like the first substance I run into is the carbonate ions, so those are my strongest base. So I'm going to take both of those and react them together. Now, looking at my table here, so I'm going to erase what I didn't use. So if I look and compare the positions of the hydronium ions with the carbonate ions, you can see that my acid is above my base, which means that I can draw this downhill line. So if I make it super obvious here, there's the downhill line. So acid is above the base. That means products are favored or the forward reaction is favored. But since we were told that this was a quantitative reaction, I'm only going to use this arrow. Okay. Now, remember we have this as our acid, this as our base. So acid A for away, only one proton gets transferred. So then my products are going to be, so if I imagine hydronium with one less hydrogen, that's H2O, so that's water. And we started off with a +1 charge. We lost that hydrogen ion, so that's why water is neutral. Now for my other product here, so I need to imagine my carbonate ion, but with one more hydrogen, so that's going to be HCO3, 1- aqueous. So how I'm getting the charge is I started off with -2, I gained a +1 charge, so that's going to give me -1. Okay, and now I'm going to label these here. So I'm going to change the coloring on this to base. Okay, so acids, they are always paired with a conjugate base, and bases are always paired with a conjugate acid. Okay, And those are those two examples finished.